Alright, this video lesson is taking a look at how we can use graphical analysis to determine the rate laws and rate constants for different chemical reactions. This has a lot of applications in industrial chemistry and allows the chemist to determine what later on in the next series we'll look at how we can use this analysis to determine what is actually driving the reaction, what mechanisms are involved, and which one is the rate determining step. So if you're producing chemicals and things like that, you're running a process, so you're working in a mill or a chemical plant, any type of industrial application where there's chemical reactions, it's really important to understand the nature of the chemical reaction so you can optimize production and things like that. If this is the first time you're seeing this video series, you may want to pause it right now to write down this data table. We're going to take you through an activity where we've got three different reactions, and in each case we've got a reactant. We've got reactant A in one reaction, reactant B in another, reactant C in the third, and each of these reactants are decomposing. And what we've done over time is we've looked at the concentration of each reactant over time, and we've seen how that the concentration is changing. And we're going to do a little activity where we're going to graph each reactant's concentration over time, and we're going to try and determine if there's a type of graph we can use that will give us a nice straight linear relationship, a line, because if we have a line, then we can analyze the graph using the equation of the line, y equals mx plus b, and using that information we can start to predict what concentrations will be at certain times in the reaction, which will give us the ability to sort of optimize optimize the conditions for the reaction, things like that. Now, just doing a straight concentration time graph may not work, so we're going to use a couple extra tricks here. We're going to generate three different graphs. We're going to generate a concentration versus time graph, and that's the first one. We're also going to generate a ln of concentration over time graph, and that's a little button on your calculator. It's got an ln, and if you type a number into it and you hit the ln, you're going to get another number out. Now, we're not going to go too deep into what that button does and sort of what the math behind it, but it is a math tool that we can use to look at values differently. And we can also, the third graph is going to be a 1 over an inverse graph. So you would take your concentration, whatever it would be, and you would take the number 1 and divide it by the concentration. So an example of this would be, say, at 8 seconds for concentration A, or reactant A, sorry, when its concentration is 0.176, if you were to do a inverse concentration over time graph, what you do is you would take the inverse of 0.176, so 1 divided by that, and compare that to the time at 8 seconds, and that would be your points on your graph. So at this point, I'll pause the video so you can take the time to make the three graphs for reactant A, for reactant B, and reactant C, and we're going to take a look and see what different relationships are possible here. Okay, so I'm assuming at this point you've got the graphs done. If not, quickly pause again. And what we're going to do is we're going to start to take a look at the results we get for each different type of graph. So, reactant. So we'll take a look at reactant A here. And so for reactant A, you should have graphs that look very similar here, and I've sort of done some extra work on here, and I'm going to take you through it. So your concentration versus time graph, which is the first one we're going to take a look at right here, when we take a look at this, we see that we already get a nice straight line. And the nice things about straight lines is that we can find the slope of the line. And we can carry the line on, and we can find a very important point, which is right there, and that is our y-intercept. And y-intercept is really important because in the case of this graph, our y-intercept is our initial concentration. So what would our concentration be at time 0? And that's super important when we go to use the equation of the line. What you could do right now is you can pause the video. I've already shown you how I've extended the line, but you can pause the video and just determine what the slope of the line is right there. And I'm going to take you through that in a second and show you what we can use with that information. If you haven't found the slope for any of the graphs yet, for any of the other lines, when you found a nice straight line, make sure you pause the video and do that as well, because the slopes are going to be super important. As well, continue your line so that you can find the y-intercept. This is where it crosses that y-intercept. So what we're going to do right now is take a look at the relationship here. We've found our y-intercept, we've done some slope calculations, and your slope calculations might be slightly different, but you should get the same result. So we're going to take a look at what the relationship is. Now, in this case, when we go to find the equation of the line, again I'll show that y equals mx plus b. Our b is our y-intercept. Our x is our slope. Or sorry, m is our slope. And x will be a value of time, and y will be a value for concentration. And so we can see that we can derive a relationship for the concentration of our reactant at any time frame is going to be equal to the slope of the graph times the time added to the initial concentration. So let's take a look at what our values should have been. So initially we determined that by extrapolating the line that our initial concentration is 0.2 moles per liter. Awesome. So that's our B right there. What our y-intercept would be. Now our m is equal to our rate constant, and we actually use a K for that when we do these calculations. And so we're going to take a look. So I used values 0.08 moles per liter. Notice that the slope is going down, so our K value is going to be a negative. And so I picked a couple points here. So this is 0.08 and 0.152. I had to sort of guess as best as I could, and that was between 16 and 40 seconds. So there's my slope calculation, and we'll take a look here and see what we found. So plugging everything in, I get a rate constant at negative 3.0 times 10 to the minus 3. We're not going to put any units in here right now, so we're not going to worry about that right now, but it would be moles per liter per second. So that's the value that we get. And what we can do now with that is we can plug that value into our equation, and we can determine at any point the concentration of our reactant A if we take our rate constant and we multiply by the time, and then we add 0.20 moles per liter. Remember, this is what we would start at, because this is a negative number. The overall number, your overall concentration, will go down. And so we can take some time and do some predictions. And I've shown one here where what would be the concentration after 50 seconds. I would suggest that you pause the video at this point and try doing a couple other predictions, maybe at 25 seconds, or go beyond the scope of the graph and say maybe at 65 seconds, and see what your concentration would be. And actually check it on the graph and make sure that it turns out that that's correct. That's sort of your sanity check. So as you can see here, I inputted 50 in, a little messy writing, but I'm sure you can see it. And I got a value of 0.05 moles per liter after 50 seconds. When I then went and checked it on the graph, lo and behold, look at what we got right there. So again, pause it, try a couple more predictions, and see if it works on your graph. Now that you've done that, what we're going to do now is try and understand what type of relationship it is when we've got a concentration over time graph that's linear. We need to determine the order of the reaction. And in the case of this reaction, we call it a zero-order reaction for a reason. We ran some experiments, and what we did was we tried putting different initial concentrations in. And when we did that, we wanted to see how that would affect the rate of the reaction. If we, say, went from 0.2 and we halved it, or went from 0.2 moles per liter and we doubled it. And we ran the reaction experimentally, and we found that the rate of the reaction stayed the same. So if we take a look at our reaction here, this is our rate of our reaction. And look, it's the exact same rate of reaction no matter what we put in for our initial concentration. And we did this experimentally. And so what this tells us is that if we have a linear relationship with a concentration over time graph, our initial concentration has no bearing at all on the rate of reaction. And that's super important. That means we could put anything in here for our initial concentration at A, and our reactant A has no bearing on how quickly that reaction is going to take place. And as a chemist, that's super important to know what reactants are affecting your reaction. So when we take a look at our rate, the relationship between our rate and the concentration of our reactant, we want to determine what X is up here, because depending on what X is, that will let us know what effect that reactant has on the reaction. In this case, our rate doesn't change no matter what we put in for A. And so because the rate doesn't change, and our rate is going to always be equal to K times our rate constant times our initial concentration, because that never changes, then that means whatever we put in here is always equal to 1. And the only way to get anything inside these brackets to be equal to 1, then our exponent up here would have to be equal to 0, because anything to the exponent of 0 is 1. And our rate stays the same. So K stays the same no matter what we put in here for our initial concentration. So that must mean our exponent is 0, and that means we have a zero-order reaction. So our reactant has no effect on the rate of the reaction. So now what we're going to do is we're going to take a look at the reactant B, and we're just going to quickly focus on the concentration over time graph for reactant B. So this is what we get initially. And what I've done here is I put a couple red lines in here for a reason. Notice that this graph is a curved line. And what does that curved line mean? Well, the curved line means that the rate is changing. Notice that it's changing along the entire time. If it was linear, the rate would be the same, but in this case it's not. We can't find the slope of this entire line because it's curved. What we can do is pick points on the curve and draw a tangent to that point, and we can find what we would call the instantaneous rate of reaction. So if I were to take a look at this tangent right here, that red line, I can use that red line. I can calculate slope. But by me calculating the slope, that's going to be equal to the instantaneous rate of reaction. And we can see qualitatively here that we've got a great rate of reaction here, and then after time it's starting to flatten out, so our rate changes over time. So let's take a quick look here. We'll go into further analysis and actually take a look at what we can find mathematically. So what I've done is I've broken this up into two stages, stage 1, stage 2, and I determine my instantaneous rate of reaction at 4.3 seconds and then again at 12.2 seconds. So I put in my change in my concentration over my change in time, and of course, because my concentration is going down, I'm going to get negative values. Initially it's 0.012 moles per liter per second. Which is pretty fast, and then notice how drastically it drops. About 8 seconds later it's down to a much lower rate of reaction. So we know that our reaction is changing over time, the rate that's changing over time, which would make sense that it would slow down as you start to lose more and more of your reactants. So let's take a look here and see why this is, or how we can use this to try and determine a relationship. So one of the tools that we can use is this little button on our calculators called the ln button. And the ln button takes our number and flips it into a different base set for that number. So it's not based on zeros and ones, twos, threes, fours, all the way up to 10. It's based on a different system of numbering. But when we ln it, we will find that our graph is going to change shape, and we can use that graph to determine the equation of the line. Now the equation of the line, when we ln things, still stays the same. This is still y, this is still mx, and this is still b. All we've done here is we put a ln out in front of our concentrations. So if we were to flip back to our zero order reaction, so we've got concentration whenever we want is equal to mt plus a, our initial concentration of our reactant. When we flip to here, we see the same thing. All we've done here is we've put this little math tool out in front, and that's all I want you to think about the ln right now. It's just that's a little math tool. It's going to help us redefine a relationship. One of the things that we will do when you do ln, it will flip the signs a little bit. Usually our rate constant is a negative because our rate is getting we are getting lower over time in terms of our concentration. But it's much easier when we do the math for lnning that we just make our mx or our kt a negative. And you'll see why that's the case in a second. It just helps your numbers come out in a much better format. So all we're going to do is rewrite this relationship right here to be ln of our B concentration whenever we want is equal to ln of our initial B concentration minus KT. And what that does is then we can use a positive value for K whenever we want. We call K actually an absolute value. And this is important because for this is what we call a first order reaction, and there's second order reactions, and the math works best when K is positive. So we're going to take a look at the analysis of all three graphs now for reactant B. So if we were to, like we showed you before, just do the graph for the concentration of B over time, we get this curved graph, can't use it. The rate of change, the rate of reaction is changing over time. If we ln all of our concentration for B values and then graph that, we get a nice linear relationship. And we can do everything that we did for the first graph, or the first reactant for A, but we're now going to do this for the ln versus time graph. So at this point, if you haven't calculated slopes or the y-intercept, I want you to take a second right now, pause the video, and make sure you do that. Okay, now we're going to quickly check out what the relationship is here. So here is our equation that I showed you before. If I ln my value for ln of initial concentration, I've extrapolated it to be negative 1.6, and I'll pull this down a little bit further here, and we can see what the slope calculations net us. So again, I use my values along here. They're definitely different than the values that you see here. When you ln, all your values become negative, which is why if we make K a positive, in the end, things work out nicer. So what we get here, we plug our values in. I pick some values along the line, and I calculated the slope for that, and I got my slope to be equal to negative 0.1. So what can I use that? What can I use that for? Well, I can plug my y-intercept and my slope value into the equation. And so from doing that, I get this as the relationship. Ln of my B concentration is going to be equal to negative 0.1 t. So take this, multiply it by whatever time you want, minus 1.6. Now, if I actually want to find a value, though, I have to get rid of my ln. And so what if I plug a number in here? Say, what would be my concentration of B after 16 seconds? Well, I would plug my 16 in for t. We can see that relationship right here. Alright, and I still have my 0.1, and I still have my minus 1.6. And I get a value here, negative 3.2. Now, on your calculator, you're going to see an e to the exponent button. The only way to get rid of a ln is if you put everything to an exponent. So whatever we have numerically on this side, we have to put that to the exponent. So we can find your e button, and if you type in e to the exponent minus 3.2, you're going to get a number, and that number is going to correspond with the actual concentration for B at the time of 16 seconds. So we can get rid of the ln by using that function on our calculator. Maybe take a second right now and pick a couple other points on the graph, maybe extrapolate one point within the graph so you can test and see if it works out. It did in this case. 16 seconds did give us a concentration of negative 0.41. Try another graph, try another point along the graph and one outside the graph and see if you get the correct results. What we're going to do after that is take a look at some more experimental data and see if the rate of reaction was affected by changing the initial concentration. Okay, so at this point you've done some more predictions, plugged some more values in, practice using the different functions on your calculator. So let's take a look at what happens here. When we take a look at changing the rate of changing the initial concentration, we start at 0.1 moles per liter and we changed it to 0.2. We notice something happening here. The rate doubled. When we went from 0.1 to 0.3, the rate tripled. So what this tells us is that our rate is dependent upon the initial concentration of the B reactant, and that if I double my initial concentration, I double my rate. If I triple my concentration, I triple my rate. So what this means is my rate is dependent on my rate constant times my initial concentration of my reactant to a certain factor. And because if I double it, it doubles, then that factor, x, that exponent is going to be 1. And so we call this a first order reaction. So our rate of the reaction is always going to be equal to our rate constant, which we got over here, our slope, times our initial concentration to the power of 1. So rate constant times the initial concentration. And our rate constant is 0.1. Multiply that by 0.1 as our initial concentration, and we get 0.01. Take our rate constant of 0.1, multiply it by our initial concentration of 0.2, and we get 0.02. So this allows us to see what that relationship is like. At this point, we're going to go to our last reaction, and that one was C, reactant C. So again, what I would like you to do, if you haven't done so already, pause the video and make sure you determine the slope of your straight line. In this case, we had a curve relationship for our concentration time graph. We did the ln of our concentration versus time, and we still got a curve relationship, and so we had to go to an inverse relationship of concentration versus time, and now we finally got a nice linear relationship. Notice that the inverse relationship, the slope is positive, whereas the last two, the slope was negative. But that's what happens when you inverse the concentration. So let's make sure you've done the slope calculations and the y-intercept calculations. I found it right here. We've got the y-intercept is 5. And let's take a look quickly here at what our equations are going to look like. So our equation of our line, which is y equals mx plus b, our y value is right here. Again, our mx, or in this case mt, because our x is our time. And then our b is going to be 1 over our initial concentration, which you see right here. So now, let's see what we got. So our rate constant, which is our slope, I plugged some numbers in to determine it, and I got a rate constant of 0.1. I then wanted to find my initial concentration, and 1 over C is equal to 5 over 1. Now if I take that and want to actually determine what the initial concentration is, I have to flip 5 over 1 to 1 over 5. And I get initial concentration of 0.2 moles per liter. So you can't take the 5 and plug that into the equation here. Alright? 1 over C is equal to 5. But our initial concentration in the real world would actually be 0.2 moles per liter. Now let's take a look and see if we could use this to make some predictions. So what I've decided to do is determine at 180 seconds what should the concentration be. And so I use my formula. 1 over Ct is equal to 0.1 T plus 5. Alright, so I still use my 5 value in the equation, but in real life I know my initial concentration. That 5 represents an initial concentration of 0.2 moles per liter. Now I would like to find out what my concentration of C would be after 180 seconds. So I plug everything in, and just simple math, and I get my 1 over concentration over time, or my inverse of concentration for my time, is equal to 23. In order to figure out what that concentration is in real life, I would find the inverse of 23, which would be 1 divided by 23. So in the real world, that concentration would be 0.43 moles per liter. Now if I take a look at 23 right here, and I look at 180 seconds, it looks like we're pretty much bang on right there. Now, again, we're going to repeat the same reaction using different concentrations for your starting points. And let's take a look at what we find here. So these are my 3 initial concentrations, and I doubled and I tripled from what I started with. And my rates of reaction are vastly different than the last two. When I doubled my initial concentration, my rate of reaction went up by a factor of 4. When I tripled my initial concentration, the rate of reaction went up by a factor of 9. You can probably figure out pretty quickly what the relationship is. If I double something, it goes up by 4. Obviously, I have a squared relationship. If I triple something, it goes up by 9. That would be the same as 3 to the power of 2. So when we take a look at how to determine my rate law is equal to K times my initial concentration to the power of X. Well, when I double something and the rate goes up by 4, then obviously I know that I need to put a 2 there. So that in order to determine the rate of the reaction, I take my rate constant, which is 0.1, I multiply it by my initial concentration, and then that, because it is a squared or a second order reaction, I need to square that initial concentration. And so in the next video series, what we'll be doing is taking a look at how you can use changes in initial concentration and the rate of production of your product, and determining what order each of the reactants is for that reaction. So that will be in our next video series.